So the last video left off with this slide where we talked about the right-hand rule. Now, I want to begin by being very explicit that there are two versions of the right-hand rule. One version of the right-hand rule allows us to find the direction of a magnetic field created by a current. The other version of the right-hand rule is for finding the direction of a force on moving charges in a background magnetic field. So, when we are trying to find the right-hand rule using showing the direction of a magnetic field due to a current in a wire, what we have is we have one straight part and one curly part. The straight part is always going to be aligned with our thumb. The curly part is always going to be aligned with the four fingers. Now notice in this picture that if you were to stand up here and look down, so from your perspective, the current is coming towards you, you would see your thumb is pointed at you and the magnetic field created by this wire wraps around the wire in a counterclockwise direction. If you were to stand down here below the wire and see the current going away from you, you would see the magnetic field be pointing around the wire in a clockwise direction. And this is always true. So for example, if you are on this side of the wire, the magnetic field is coming out of the computer screen. If you are coming on this side of the wire, the magnetic field will be pointing into the computer screen. From your perspective, where you're sitting watching this video right now, in front of the wire, between the wire and you, the magnetic field is pointing to the right. Behind the wire, from your perspective, the magnetic field is pointing to the left. So the magnetic field wraps around the wire and it has a different direction. Its direction depends on where are you in relation to the wire. So now very often to deal with problems in magnetism, we need 3D and we need a way to represent three directions on a sheet of paper. So the convention we use is a circle with a dot inside it indicates a quantity that is coming out of a page. A circle with an X in it indicates a quantity that is pointing into a page. So, for example, if the current in a wire is coming out of the page and moving towards you, I align the thumb of my right hand with the current, so I have my thumb pointed towards me, and I notice that my four fingers are wrapping counterclockwise around the wire. So the magnetic field created by this wire will be pointing counterclockwise. Take a moment, convince yourself this is indeed the case. Now remember, make sure you're using your right hand. For me, that's the hand I write with. I'm not left-handed, so it might be the reverse. That is one common mistake people make early on. The right-hand rule is sometimes awkward to get used to, but just practice it and it becomes okay very fast. Now, let us suppose we have a wire that is in the plane of the computer screen and current in the wire is flowing to the left. Well, what direction is the magnetic field going to be pointing? Take a moment, think about it, see if you could come up with an answer. So, to answer a question like this, I am going to kind of do this piecewise. I'm going to say, if I'm above the wire, what direction will the magnetic field point? If I'm below the wire, what direction will the magnetic field point? If I'm in front of the wire, what direction will the magnetic field point? So I align my right thumb so that my right thumb is pointing to the left in the direction of the current. When my fingers are above the wire, my fingers are pointing into the page. When my fingers are below the wire, my fingers are coming out towards me. And if my fingers are in between the wire and myself, so if my four fingers are in front of the wire, from my perspective, my fingers will be pointing upward. So the magnetic field will come out of the page, point upward, go into the page above the wire, and be pointing down if you are behind the wire. So again, this is a little awkward at first, but just practice it, and I promise you it will be awkward, then it clicks, and then it becomes very easy. So this is one variation of the right-hand rule with magnetic fields, where we always have a straight part and we always have a curly part. Now, I am intentionally not saying the current is the straight part, the magnetic field is the curly part, because later on in this course, I'm going to change those two, but I'll still have a notion of a straight part and a curly part. So what we're going to see later on is we'll have a circular loop of wire and the magnetic field. So the circular loop will be my four fingers, the current, and then the magnetic field will be my thumb. But we always have a straight part and we always have a curly part. Now, we talked about how do you find the direction of a magnetic field, but how do we find the strength of the magnetic field? So I have a notion of direction, but what about the magnitude of this vector field? Well, it seems reasonable to expect that if we're close to the wire, the magnetic field should be really strong. If we're far away from the wire, the magnetic field should be fairly weak. So the strength of the magnetic field is given by this equation. Magnetic field strength is mu naught I over 2 pi r. So magnetic fields are measured in Tesla. 1 Tesla is the SI unit of magnetic field. Sometimes they're also measured in Gauss. I'll always work in Tesla. Whenever you're doing a calculation, you should always be working in Tesla. But sometimes the book will use Gauss as well. I will only use Tesla for exams. That's the common one to be used. Now, within this equation, first of all, this equation applies only to the case of an infinitely long straight wire. So if we have a wire that is not really, really long or not straight, we need some other equation to use it. But this is the common example we'll be considering. So here, I is the current flowing through the wire, just like we had V equals IR from a few chapters ago. Same thing as current that we always been talking about. R is the distance from the wire, so the distance perpendicular to some point. So R could be this distance or R could be this distance. Basically, how far away from the wire are you? And mu naught is a constant of nature. So in the same way that we had epsilon naught when we were talking about the strength of electric fields, mu naught is known as the permeability of free space, and mu naught is just a constant of nature for magnetic fields, very much in the same way that epsilon naught was a constant of nature for electric fields. And then 2 pi is just a number. Now, what about the magnetic force? A magnetic field, I said, has both a magnitude and a direction at every location in space. And magnetic fields are created by moving charges. So here's a magnetic field, and let's, for the sake of this discussion, assume that this magnetic field was set up by some arrangement of electrical currents. So we have some wires that are carrying currents. These wires are not shown, but these wires somehow set up a nice uniform magnetic field. Now, right now, I don't expect you to know how you could arrange wires to set up a nice uniform magnetic field. In the future, we will discuss how you could do this. It's really not that difficult. Kind of like setting up a uniform electric field. All you have to do is get 2 metal plates and put charges on the plates, put the plates close together, basically build a capacitor. A capacitor is a simple device. To create a magnetic field like this, you would use a solenoid. A solenoid is like a capacitor, just a really simple arrangement of wires. So it's not really that hard to create a uniform magnetic field. But I create a uniform magnetic field. Let's place a charge in this magnetic field. Now, the charge might feel a magnetic force. So what will the strength of the magnetic force on that charge depend on? Well, when we were talking about the Coulomb force, when you place a charge in an electric field, we said the Coulomb force depends on the charge of the particle and the strength of the electric field. The particle sees an electric field due to some other stuff, and then that particle will feel an electric force. And we have the force on that particle was given by F equals QE. Well, For a particle in a magnetic field, that particle might feel a magnetic force, and the magnetic force on the charged particle depends on how much charge the particle has. The magnetic force will depend on the strength of the magnetic field. So right now, the magnetic field kind of looks like the electric field. But if you think back to one of the previous videos, I said that the magnetic force or magnetic fields are, in a way, they don't really exist. A magnetic field is just a manifestation of an electric field as observed by a moving observer. So to truly reconcile magnetism and electricity, you need to bring in special relativity. Special relativity is just if you are moving, you see something. If you are stationary, you see something different. And special relativity is a way we could have a coherent set of physical rules that describe both possible observers. So if magnetism is a result of motion, then it seems reasonable that the strength of the magnetic force should also depend on the velocity of the particle. So velocity is both speed and direction. So velocity, speed, how fast are you going? And velocity, well, that's speed and direction. I'm kind of being redundant because I mentioned speed up here. So the direction of the magnetic field, the direction of the magnetic field is to the right. The direction of motion is down and to the right. So we have some angle between the direction of B and the direction of V. And this angle will affect the magnetic force on a charged particle. So the equation for the strength of the magnetic force is given by this, QVB sine theta. So here Q is the point charge, how many coulombs of charge does the particle have? V is the speed of that charged particle. B is the strength of the background magnetic field. And theta is, as I said, the angle between the direction of motion. If you think about it, the direction of motion is always going to be the same as the direction of velocity, and the direction the magnetic field points. So as I said, the magnetic field points to the right. The direction of motion is down and to the right. So the strength of the magnetic force is going to be affected by this. Now looking at this picture a little more, I notice the sine of theta. Sine of 0 and sine of 180 are both 0. So if the direction of motion is in the same direction as the magnetic field, then you'll have a force of 0. And if the direction of motion is perpendicular to the magnetic field, we get sine of 90, which is equal to 1. And that tends to maximize the strength of the magnetic force.